Hi, welcome back again. So today we'll be finishing chapter 13 as well as starting chapter 14. So we'll finish the reminder sections in chapter 13, mainly phase changes, and then how we can use diagrams to identify different phases and where phase changes. And then in chapter 14, we'll start with the concept of heat and talk about heat capacity. So let's dive in. The last a couple of sections in chapter 14 or 13 is really just I would say just review of what you guys have learned already in chemistry. So we all know that substance or materials have different phases. The common one, water, that you get we are we or at least we think we are very familiar with is um, normally having like different phases like vapor, in forms of liquid or in form of solid, we call it ice. Okay, but water actually have more than three phases. Okay, so more than that you can imagine, or you could be um, aware of. It has also have very strange features. Okay, all right, but those three are very common phases for most substance. Now, a lot of times we can use diagrams to represent different phases of a substance. So for example, if you have a VT diagram, volume versus temperature diagram, so if the diagram is a straight line, then this is a gas, ideal gas behavior, because for ideal gases, PV equal to nRT. So V and T is proportional to each other if the number of gas is not changing and pressure is not changing. So R is a gas constant. Okay, so in that case, now if the diagram is not so in this case, if in the region it's straight line, we know it's in gas phase. Now if it's not, so then it will be not straight line. So it will be like having certain curve here. So in this case over here, it condensed into liquid and then freezes to solid here. Okay, so this is the case for um, a particular gas here was carbon dioxide. All right. Uh, Not necessarily carbon dioxide, but it's a certain gas here. Okay, so it's not clear. I don't quite remember if it's carbon dioxide, but um, for different stuff, they freeze at different temperatures. So for water, it freezes at 0 degree. For carbon dioxide, it freezes at minus 78 degrees Celsius. And then for nitrogen, if it turns into liquid form at minus 196 degrees. Okay. All right. Other diagrams, mainly you have different axes. So for example, you have a pressure versus a volume diagram, then it's called a PV diagram. So if in that case, if for gases, if you look at the ideal gases, we know PV equal to nRT. So P versus V, so P times V, then it's inverse proportional to each other if T is constant, right? And N is constant over here. So then you'll get a hyperbola curve like this guy here. So you will know that at this condition of temperature 5, then it's going to be in gas form, or also this guy, this is a parabola 2, so in temperature equal to 4, okay? And then if it's not smooth hyperbola curve here, then you see there's a phase change there, okay? So for example, if you have this curve over here. So it's initial liquid here, part of the hyperbola, and then there's a kink here, and the curve turns here. So then there's a phase change into liquid, and then later on it becomes vapor again. Okay, and then similarly over on this case as well. So if it's smooth curve, then it's an ideal gas. Now in this case, this is not ideal gas because there's a kind of bump in the middle here or here, and in this case, okay. All right. So certain terminologies here to remember critical point that is also called the critical temperature above which liquid cannot exist. Okay. So in this case, if you're above this point, okay, this is the critical point, then it's all in gas, it's not in liquid. And in this case, it will be somewhere here, above here, it's liquid, gas phase. All right. Critical temperatures and pressures can be found in this table for certain substances. If you ever need them, you can look them up here. A specific diagram is called the phase diagram, which is you actually plot P versus T. So it's a PT diagram, but it's called phase diagram. So in that case, you can find the region where under certain condition, if the object of the material is in liquid form, in vapor form, in solid form. And there's a particular point called triple point where those three phases can coexist. So that's called triple point. Okay? And in this, after this critical point over here, then it cannot be liquid. Okay. Again, that's what we talked about in the previous slide. When a substance is in liquid form, and this liquid is also in equilibrium with the vapor form of it in above. So what happens here is the liquid is vaporizing at the same time the vapor on top is condensing in becoming liquid. So these two then becomes equilibrium. It's not like these two are not happening, but they are actually happening at the same time, but in the same rate. So they are having equilibrium. Okay. And a term called vapor pressure is defined at which pressure that the gas coexists with a solid or liquid. And vapor pressure determines the boil temperature of the liquid. Okay. So if you have different vapor pressure, then the liquid could be boiling at different temperatures. So for example, if you have different atomic pressure at different elevations, then the boiling temperature of water will be different. Okay? So at elevation goes higher and higher, water actually boils at smaller and smaller temperature. Okay. So over here, if you are, this is the sea level at atmospheric pressure at 100 degrees Celsius. If you are at 10,000 feet above sea level, then it drops to about 90. And then, however, if you are using a pressure cooker, which could be having higher pressure, 2 times our atmospheric pressure, then the boiling temperature will be 120 degrees above it. So that we know if you, so cooking is all about chemical reactions, right? So if you are cooking at higher temperature, then chemical reaction happens faster. So then you can cook stuff easier or faster. So pressure cook will use less time to cook than the normal, if you have normal pot or container. Now, if you go to higher elevations, your atmospheric pressure drops, so then you'll have to cook longer. So for example, if you go to Denver, which is a mile above the sea level, so then the 3 minutes egg cooking rule will not apply. You have to cook longer in Denver. All right. Also, partial pressure, this refers to when you have a container that have a mixture of gases. So for example, air is a mixture of oxygen and nitrogen with some residual other gases, but the main components are oxygen and nitrogen. Okay, so then depends on what's the fraction of those, or specifically mole fraction of those gases, then the pressure comes from those gases in percentage according to their mole fractions. So the contribution of the total pressure from each of the gases called partial pressure. Okay, so this is also called Dalton's law. A few terminology here. I'll just encourage you guys read through the PowerPoint slide and then also the textbook if you want to have more information, but we'll just skip that. Okay. So now let's start chapter 14 on heat and heat transfer method. Okay, so we'll be just focusing on heat today and heat capacity. So when we drink soda, right, we would like to have ice in it so that will give us better taste. But the process happens here is you actually have heat transfer between the soda and the ice cubes itself. Okay, so these two are not having the same temperature, so then there's a exchange of energy we call heat. Okay, so this is the definition of heat. Heat is the spontaneous transfer of energy due to a temperature difference. Okay, so heat is equivalent to change of energy. So again, imagine then heat, we use Q for the symbol. Its unit should be the same as the energy in joules. All right. And once these two reach the same temperature certain time later on, then the heat transfer process ends. Okay, so there's no more heat transfer because the two now has the same temperature. There's also units called calories. You guys hear it often, but it's not the SI unit. The SI unit for the heat is joules. In between joules and calories, so 1 calorie is about 4.186 joules. Specifically, um, for a joule, it's defined as the 1 gram of water at 14.5 degrees increased by 1 degree to 15.5 degree. Okay, and the conversion between the calories to joule is that. Okay, oh, actually, I'm sorry. 1 calorie is defined as the amount of energy that is needed to change the temperature of 1 gram of water by 1 degree from 14.5 degrees to 15.5 degrees Celsius. All right. Heat and energy or mechanical energy equivalent. So that was originally demonstrated by James Joule. So then due to his contribution to the field of thermodynamics, then his last name was honored um, to be used for the energy, the units of joules. Okay, so this is a demonstration. So this is there's this setup over here. You have two weights here, and they can be dropped to a certain distance, each the same distance over here, and then mechanical energy change or gravitational potential change is used to turn into the mechanical energy of this stirrer. And at the end, you can monitor the temperature change over here. You can calculate how much energy is transferred into this system, which is the heat needed to increase the temperature of this guy. You can calculate how much heat is that. So it turns out the heat um, that is needed to increase the temperature of the liquid here equal to the gravitational potential energy change of these two weights. Okay, so in that experiment, then mechanical energy equivalent to heat or energy equivalent to heat is being demonstrated. All right, so if you have heat added to a material, a substance, then the substance will have energy change. So, or temperature change. So Q, heat added to the object, then corresponding to the temperature change, delta T. And it has to be do with the amount of the substance you have in the mass, in form of mass. And then also this C, small c here is called the specific heat capacity or just specific heat. So this C depends on materials. Different materials have different C, which is a constant number for the materials. Um, specific heat is in the SI units of joules. So you can see here, this guy is joules. It's in the joules over Kelvin, kilogram times Kelvin. So this is in joules, this is in kilogram, this is in Kelvin, okay? And because this is delta T, so it's equivalent to have degrees Celsius, okay? So these two, either this one or this one, they are the same because in the equation, it's delta T there. Specific heat C is in the SI unit of joules over kilogram times Kelvin or joules over kilogram times degrees Celsius. Other units, sometimes you may see it as be calories per kilogram times their degree C or Kelvin or kilocalories. Okay, so just in the place of joules. You need to do the unit conversion sometimes there. All right. So here is the table of specific heat for materials, certain materials, both in joules per kilogram times degree Celsius or kilokelvins over kilogram times degree Celsius. One thing that stands out here is water. Water actually has very high heat capacity, 4186, which is 1 kilokelvin. Okay, so 1 kilocalorie is 4186 joules. And that's why water is often used as coolant. So in your car, the water is used as coolant for most of it. Most of the um, substance in the coolant is made of water. That's because of its high heat capacity. Okay? And metals will typically have lower heat capacity compared to other materials. All right. So once there's a heat exchange, or you add heat to the substance or take heat out from the substance, then the temperature will change. Okay. So the application of heat capacity for materials, because as I mentioned earlier, heat capacity is a constant number for for different materials. So if you can determine the heat capacity for an unknown substance, then you can identify what the unknown substance is. Okay. So the application of this is a device called the calorimeter, which is lightweighted, and it's an insulate container, typically using water, and you can now put another material into this calorimeter. So for example, a metal, a heated metal or something else. And then you can measure the initial and final temperature, and then calculate what will be the heat capacity of this unknown substance to identify that substance, okay? All right, so you'll measure the final temperature, um, the equilibrium temperature. This is for both the object and the water. And you'll calculate, because basically what happens here is there's heat transfer between the liquid you see here, water, and the substance. Okay, so one will be cold, one will be hot. So heat received by the cold object, it should be positive. So these two add up should be equal to 0 if you have two substances involved, one being the unknown substance, the other one being the liquid. Okay. Now, in such scenario, it might be more complicated. You might have three objects. Okay, so then there'll be heat either added to a certain object or taken out from the object, or maybe there will be two objects receiving heat, one object that gives out heat, or maybe two objects gives out heat, but one object receives the heat. So in different scenarios. But if you just have two objects here, then one will be taking the heat, one will be giving out the heat. So this guy then will be minus. So the positive plus the minus should be equal to 0. Okay, so you'll start with this one, and then you'll calculate the specific heat of the unknown object. We'll take a look at the one example here that gives you how this is being done. And then in this scenario, it's asking then the other way around. It's asking for the final temperature of the system. Okay, but it already gives you the substances. One is being lead, the other one being water. Okay, so then we can look up for the specific heat capacities, and it gives us the initial temperature for the lead is 81.2 degrees Celsius. For the mass of it is 225 grams. For water, it's 20.3 degrees Celsius, and its mass is 155. Okay, given the heat capacities of the two, for lead 128, and then for water 4186. Okay, so we are looking for final temperature. All right, so let me use my other camera over here so you can see how you can solve for this problem. I'll write down the nodes we have first. So we have temperature of lead. I will use temperature and the chemical symbol here for the subscript, 81.2 degrees. Temperature of water, H2O, is 20.3 degrees. Okay. Heat capacity of lead is given as 128 joules kilogram degrees Celsius. Heat capacity of water is 4186 joules kilogram degrees Celsius. Okay. And the two masses are given. Mass of the lead, again, 225 grams. Mass of the water is 155 grams. Okay. And we are looking for T final of the equilibrium. And I'm going to just stop sharing so you can see the solution better here. Okay, so we'll start with Q of the lead, right? Plus Q of the water. These two should add up to be 0. So one of them should be positive, the other one will be negative at the end. Now for Q of the lead, if we remember for the heat capacity definition, Q for a certain substance is MC delta T. Okay, so we're going to apply this to this guy, lead, and then this to also water, and then add them up to be 0. Okay, so in this case, we'll say then for lead, this will be mass of the lead, heat capacity of the lead, and then temperature change of the lead, right? And then plus mass of the water, heat capacity of water, and then temperature change of the water. So that should go to 0. Okay. So in here, temperature change for the lead, it should be, we know this. Okay, now let's work on this. So mass times PB, C times PB, temperature change will be final temperature of the lead, right? And because the lead and water are in contact, so final temperature lead and water are the same, so I will not distinguish between TF for the lead and then TF for the water, so they are the same. TF for the lead is the same as TF for the water. We'll just say TF, okay? So minus the initial temperature of the lead, okay? And then plus mass of the water, C of the water, times T final minus T of the water equals to 0. So basically, now in this equation here, we know the mass of this guy, we know this guy, we know initial temperature of lead, mass of the water, C of the water, and then this, right? The only unknown here is the TF, and that's what we are looking for, but there are two of them. So we will combine them together. So you can see here, you'll do distribution of these two into the parentheses, and then also these two into the parentheses, okay? So we'll get MPB, let me move up a little bit here, CPB, TF, right? And then minus MPB, CPB, TPB here, plus MH2O, CH2O, TF minus MH2O, CH2O, and TH2O. That goes to 0. Okay, so combine these two that has the unknown that we are looking for, and then we'll move the rest to the other side of the equation, right? To the other side of the equation, to the other side of the equation. All right, these two combined, they are both positive. TF, TF. So then we'll add these two up. Okay, so we do MPB, CPB plus MH2O, CH2O, right? Both together times TF equals to minus, go to the other side, become positive, minus goes to the other side, become positive. So MPB, CPB, TPB, okay? And then plus MH2O, CH2O, and TH2O. All right. So T final here then should be equal to all this divided by this, right? So it should be that MPB, CPB, TPB plus MH2O, CH2O, TH2O divided by MPB, CPB plus MH2O, CH2O. Okay. Now, at this point, you can plug in all the numbers and then calculate for your T final. Okay. And now, normally you think that you need to convert TPB because it's given as Celsius, right? Not Kelvin. Kelvin will be the SI unit, and then also this guy is Celsius. You might want to convert into Kelvin, but it actually is not necessary because here we are using delta TB here. Okay, so we know that delta T, the change in temperature in Kelvin and change in temperature in Celsius, they are the same. Although we break up them later on, but once you have seen that it start with that, those change in temperature, you actually do not necessarily have to convert the initial temperatures to the Kelvin first, okay? Because at the end, when you do the difference in temperature, it will be either Kelvin or Celsius, they will be the same. Okay, so you don't necessarily have to convert, but you can convert into Kelvin first and then come back or at the end convert the final temperature back to Celsius. It will turn out to be the same. Okay, so and then that's something you can do to just verify what I said. Okay, but you don't have to do that. So we'll just plug in numbers right here right now. So we'll do 225 grams, 128 joules over kilogram degrees Celsius times 81.2 degrees Celsius plus 155 grams, 4186 joules over kilogram degrees Celsius, and then times 20.3 degrees Celsius over, altogether over 225 grams times 128 joules kilogram degrees Celsius plus 155 grams, 4186 joules over kilogram times degrees Celsius. Okay. At the end, you'll get 22.9 degrees Celsius. Okay. And this should be your final answer. Now you can double check, should be in between the two initial temperatures, right? So here and here, and the final answer is 22.9, which is close to 20.3, because water has much higher heat capacity here than the lead. Okay, so then you should be getting a number closer to the water here. These two are more or less comparable for their masses. Okay. Also, you might notice that this is kilogram, but normally we do, this is gram, normally we'll do kilogram. So you can convert those into kilogram, and then at the end, you'll actually get the same answer here, because if you do conversion, this term will be multiplied by 10 to the negative 3. This term will also be multiplied by negative 10.3, and then this one as well, this one as well. So it's basically all the terms multiplied by 10 to the minus 3, so that kind of cancel out. Okay, so this then will be your final answer for this guy. Okay, so let me see if I can zoom out a little bit so you can see the full solution. Maybe a little bit hard to do. You can capture almost all of it. Okay, kind of there. Okay. All right, it's just missing the original temperatures. Okay. So we'll go back quickly to the PowerPoint slide. All right, so that'll be about it for today, but just quickly summarize what we learned today. So we have reviewed phase and phase changes, those concepts, and we look at heat and heat capacity. So basically, if heat is added or taken away from an object, then there should be a temperature change, okay? And application of it will be the calorimeter, which you can use to either find the final temperature or the system, or you can identify the unknown substance by um, um, solving for the heat capacity and then look in the app for that substance. All right, that'll be it for today. I will see you guys next time. Bye.